Hi, Sandra here. The choo-choo that you're hearing in the background is not a steam train. It is coming from this very building. And inside there is a beautiful beast. Let's go have a look.
This terrifyingly impressive machine is the perfect subject for demystifying two fascinating fields of technology at once. Have you ever been in front of a steam engine and found it simply magic? Unable to decipher how all the mechanical parts interact? And have you, like me, always wondered how electrical power plants transform rotation into that sweet juice that comes out of the electrical outlet in your house? Then this and the next video are for you, bringing you back to 1904, a time when you could still see what's going on inside machines. Welcome to the electrical steam power plant at Gaswerk Schlieren. Built 120 years ago, this behemoth is still capable of powering today's appliances, producing electricity that easily converts to Switzerland's modern regular power grid. It consists of two parts, the steam engine and the AC generator. I'm making a video about each of them, and this is the one about the steam engine. So in this video, I'll show you why this technical marvel was built in the first place, how the steam is generated nowadays, and how thousands of parts work together in perfect harmony to become a 300 horsepower steam engine. So let's take her for a spin, shall we? So why was this steam power plant built in the first place? To find out, let's rewind time to January 1st, 1893, when Zurich incorporated 11 of its surrounding towns. Overnight, Zurich's population exploded from 30,000 to 120,000 residents. Of course, such a city needed proper streetlights. It was high time to replace the smoky oil lamps by gas lanterns, as shown here in the Gazi Museum. Over time, gas got more and more important as it found its way into Zurich's households as well. The problem is, Switzerland has no natural gas and would only start importing it almost 80 years later. Therefore, Zurich needed a bigger gas plant, or in German, Gaswerk, or as we say here, Gaswerk. So what is a gas plant? It's a factory where coal can be transformed into a variety of products, but we'll focus on the gas part in this video. To perform coal gasification, all you need is just regular pit coal, air, hot steam and heat. The coal gets oxidized by the air and steam, which results in coal gas, often called town gas, which is a mixture of mainly hydrogen, methane and carbon monoxide. Before being sent off to the city in a low-pressure pipe, this gas is stored in a gasometer, a brilliantly simple construction that uses water to create a seal. The tank shifts like a telescope, and the whole thing moves up and down, depending on how full it is. Be sure to check out the Royal Society of Chemistry's cool demonstration about coal gas and gasometers. Oh, and you might also want to watch Technology Connection's summary of those times. Initially built to produce 100,000 cubic meters of gas a day, the Gaswerk Schlieren was enlarged twice and reached a daily capacity of 250,000 cubic meters by the 1930s, operating 24/7. Working here in the early years must have been suffocating and backbreaking. 10 hours a day, 6 days a week, with only 4 days of vacation per year. Such a big factory also needs a lot of electrical power, and since the plant had coal in abundance for obvious reasons, the decision was made to also include 3 electric generators driven by coal-powered burners and, of course, steam engines. Switzerland's own coal is of poor quality due to the high sulfur content, and most of the coal had to be imported. In the second half of the 20th century, more and more international high-pressure natural gas lines were built, which has twice the energy density of coal gas. In addition, while coal gas contains deadly carbon monoxide, natural gas is non-toxic. In 1974, the city of Zurich switched to natural gas entirely, and the Gaswerk Schlieren was shut down. Today it houses a multitude of artist workshops and businesses, amongst it a large climbing gym located in the former retort house. Out of the 3 steam engines and generators, the system intended as a backup remains as an impressive witness of the industrialization era. It was restored by TGVZU, an association of volunteers who keep the machine in pristine condition.
My name is Daniel and I'm part of this society. We make 4 demonstrations a year for public viewing and let it run with steam.
My name is Kaspar Schindler. I'm here in this association of the steam engine in Schlieren. I'm mechanic and mechanical engineer, and I work at the steam production for the engine. That's the vessels, the steam vessels. I make the fire, but the fire is with gas. And I also make the catering, help with the catering. Yeah.
This is Walters. She's our rookie, the youngest in our club, and the one. Yeah, if we need some technical information, we ask him, usually.
At 18 years old, Walters is by far the youngest member of the team. He's been fascinated by the topic since childhood and has spent so much time reading about steam engines and generators that the team now looks up to him and consider him one of their experts. Many guests came to see the steam engine running on this demo day, and I tried to avoid them as well as I could while filming. Despite the busy day, the TGVZU team found enough time to show me around, and they brought me to the boiler house, where there used to be coal burners generating steam. Burning coal isn't really an option anymore these days, so TGVZU has replaced the original burners by second-hand gas boilers that they had salvaged from an old laundry shop. These beasts, built in 1975, are much easier to operate, and their exhaust is a lot cleaner than burning coal. These yellow pipes supply natural gas from the international grid, ironically the very same substance that had caused the end of the Gaswerk in the first place.
You have here in the yellow line, you have the gas coming into the burner. You have here the burner, and on the other line on top, the water is flowing into the, we call it register, and then it's heated up to steam. And I can show you the entrance. For example, this is the register which is built in the boiler. And we have tubes. Cold water is entering here, is boiled up, and the steam is leaving here to this main tube, which finally goes to the machine.
The boilers are regulated automatically by a system that the members of the TGVZU had built themselves in their spare time. If you're a regular viewer, this interface probably looks familiar to you. It has a striking resemblance to the Integra train control system, and that is because it almost is one. A member of the team who had built the system is a retired railway engineer, and he built it from scrapped Integra components, giving them a second life, now managing boilers instead of track switches. Absolutely fascinating.
This indicates the burner, this indicates the pump. At the moment, everything is off, but we have the pressure, steam pressure still inside the pipe, therefore it's red. Now I will start the vessel 1. It's a control with two touches. So we push Steuern anwärmen after Steuern betrieb. Now we see the pump, green light, pump is working. Burner is still not. You hear the ventilator of the burner. Now we start the vessel 2, that's not, we go to Kaskade. Again, anwärmen, betrieben. You see, pump is on, and burner light is already lighting, but it's not yet on. This one will come in about 1 minute, it will start the burner.
I love the fact that these pumps were manufactured in a factory that is only 5 minutes on foot from where they are standing today. That factory was closed and demolished in 1985, but this pump is kept in perfect working condition by the team of volunteers. The water, after being transformed to steam, is very hot and under high pressure. These readings translate to 100 psi and 340 degrees Fahrenheit. And on the other side of this pipe is this little machine. And that one. And of course this big one. But before we proceed to the star of the show, I really want to make sure that you understand the basics of steam engines. These adorable, fully functional miniatures were made for fun by members of the TGVZU, and they're great to explain how the steam engine principle works. You see, the physics behind steam engines is actually very simple. The complexity and magic of them comes from their many interacting parts. So let's break the complexity down, starting with a thing as trivial as my pressure cooker. It has a spring-loaded piston that goes through the lid. If I apply pressure from below with a pencil, the piston is forced up. Now let's pour a bit of water into the pressure cooker. Placing the lid seals it and makes it airtight. As I turn on the stove, the water starts to evaporate and expand, building up pressure that cannot escape the pressure cooker. The pressure begins pushing evenly on all walls, including the little piston located in the lid. The pressure inside the cooker increases and gets higher and higher than the atmospheric pressure of my kitchen. Eventually, the force that the steam applies on the piston from inside becomes greater than the force of the spring holding it down, and the piston begins to move upward. Note that no steam is escaping the cooker at this point. It's simply pushing up the piston. Towards the end of the piston is a hole that allows the steam to escape when the piston approaches its end, relieving the pressure when it gets too high. As soon as that point is reached, any excess steam escapes the cooker and the pressure no longer increases, preventing the risk of an explosion. The principle here is simple. Inside this wood-decorated chamber, a piston is sealing a cylinder. Steam enters through an opening and pressure builds up, forcing the piston downwards. A flywheel is connected to the piston. As the piston is pressed down, the flywheel is forced to do half a turn. But now the assembly will be stuck in this position. So in order to allow the piston to return back to the top, we must release the steam. The momentum of the flywheel is enough to complete the turn, and we can accelerate it again by pushing down the piston with another blast of fresh steam. The cycle repeats. To make this work, we need to let steam in and out of the piston at the right time. This is the job of the valve contained in this little brass box, which could look something like this. Red marks the enclosure of the valve, containing the steam. From the right side, fresh steam, marked in blue, presses against the valve. However, it cannot enter the valve, as the green slider currently seals the path. Behind the green slider, there is a hole marked in black, going to the piston cylinder that is located behind the valve. This is the target we want to control. If we move the green slider up, steam can flow to and through the black hole, pressurizing the cylinder and thus moving the piston. If we move the green slider back to the neutral position, the cylinder is still pressurized. However, as we move the slider even lower, an opening is created at the top end, and the black hole is now connected to the left side end of the valve, the exit, through which the steam exits the valve and thus the cylinder. This way we can pressurize and depressurize the cylinder in the way we intend. All that's left to do now is to connect the piston to the valve, making the machine automatically repeat the cycle. And this is where this genius tiny contraption enters the game, called a Stephenson valve gear. It is attached to the flywheel via two X-centers, causing the nodding movement of those guide rails, which are called the expansion link. The nut between them is named the die block. Now let's loop the footage and enter slow motion to get a better look. We can observe that in the way the excenters are mounted to the flywheel shaft, the left side of the expansion link follows the movement of the piston, lagging a bit behind. Towards the center of the expansion link, it rocks a bit back and forth, but barely moves vertically. And the right end is the reverse of the left one, anticipating the movement of the piston instead of lagging behind. Remember that the die block is directly connected to the valve, so when it's up, steam enters the piston, and when it's down, the pressure is relieved. By the way, if you have watched my video about the steamship Schiller, you have seen this one before, except I called the die block a nut there, translating the word directly from German. When the die block is all the way to the right in the expansion link, the machine runs the opposite way. Now let's look at the transition. As we move the die block to the left, the machine starts to slow, as the valve is no longer opened all the way, so less steam enters and exits the piston. As we arrive at the center, the die block is no longer moved vertically. The valve remains closed in the neutral position and the machine comes to a stop. However, as we keep moving to the left, the machine cannot start on its own. Like you need to position the pedals of your bicycle before you start to get good leverage, I first have to rotate the flywheel to get the little steam engine to a position where it can start. And that's it. That's the magic behind this beautiful mechanism. We have achieved choo-choo. Remember when I said before the valve contained in this little brass box, which could look something like this? That's because I was simplifying. In reality, the valve is double, letting steam enter at the top of the piston while venting the bottom, then reversing the process. And that also holds true for each cylinder of our beloved behemoth, which, despite looks, works surprisingly similar to its little brother. Since we're tackling the complexity bottom up, let's first look at the machine's simpler second cylinder and regard the system as a whole a bit later. We'll start at the valves. Unlike the little model, our steam engine has separate valves for letting steam in and out, but the joints linking them together couple them to produce the exact same behavior as the combined valve that we had studied earlier. Let's look at them side by side. Both machines drive a flywheel, and in both cases there is a shaft connected to that flywheel, mechanically linking its position to the valve controls. Excenters connect to that shaft, converting the machine's current rotation into a rocking back and forth motion. However, while the small machine has an expansion link, the big machine does not need that because it is designed to operate at a constant speed and never in reverse. And while the little model uses a single combined valve for both letting steam in and out, our steam engine has separate valves. The one on top letting fresh steam in and the one on the bottom letting it back out. If we observe the inlet valve more closely, we can see that it is usually closed. When the control rod opens it, it does so in a short burst, allowing steam to rush in for a short time before shutting closed for the rest of the cycle. In both machines, the steam moves a piston up and down or back and forth. And as stated earlier, both machines apply pressure on the cylinder alternatively from one side while letting the used steam escape on the other, then flipping the pressure and venting in order to push the piston on its way back. This is why it has 4 valves, the top left letting steam in while the bottom right lets it out, and vice versa. Through careful adjustment of the excenters, all 4 valves are coordinated perfectly to move the piston back and forth with great force. In both machines, the piston's shaft drives a flywheel. As observed previously, neither machine can start on its own in the wrong position. However, while you can just give the little model a gentle nudge, the big steam engine is way too heavy for this and needs to be positioned just right before pressure is applied. Another similarity is that both machines rely on huge amounts of oil rather than ball bearings for most parts. The operators have to constantly insert oil into various flasks and holes. Depending on the location, various oils with different viscosities are needed. Surprisingly, these can still be purchased nowadays. Now that we finally got the principle, let's zoom out and follow the steam on its entire path through the engine. So let's rewind to the boiler room where this pipe went into the ground. It continues here in the cellar.
Also der Dampf, der kommt hier aus der Leitung. Der geht hier rein. Und den Kondenswasser abschaltet, da wird das ganze Kondenswasser rausgeschieden, damit halt die Maschine Dampf bekommt und kein Wasser. Das Wasser sammelt sich hier unten und läuft dann über diese zwei Dinge nach draußen. Dann geht der Dampf über das Ventil hier weiter in die Leitung. Die Leitung ist leicht schräg, damit das Wasser zurücklaufen kann und über das untere Ventil auch rauskommt.
The pipe then continues to another steam separator and finally makes its way up to the first cylinder, the one that we have not looked at yet. Interestingly, the steam first goes around the cylinder before entering the main valve, where the operator can regulate the machine's speed. From there, the steam reaches the inlet valves, operates the piston as described earlier, and exits the cylinder on the bottom. Even though it's weaker than before, the steam still carries a lot of energy, so it is routed to the second cylinder, goes again first around it, then enters it at the inlet valves on the top, operates the piston a second time, and is released by the outlet valves on the bottom into this pipe. The operators can now choose two options for where this pipe is supposed to go by operating this wheel. The first option is to have it run to the condenser, where the steam is mixed with water to cool it down rapidly. This makes the steam's volume shrink by 1,700 times, according to Walters, creating a vacuum that actively sucks the steam out of the steam engine. This means that the second piston is not only pushed by the exhaust steam of the first cylinder, but at the same time also actively pulled from its own exhaust on the other side, contributing even more to the phenomenal power of this machine. This arm would then operate a pump that sucks out the water that the steam has now become. However, unfortunately, the condenser froze while the machine was off in the winter several decades ago, cracking the device, and the team hasn't gotten a chance to repair it yet. Therefore, the used steam is instead directed through the second option, leading through this pipe, and then to yet another steam separator, and finally the exhaust. So, earlier I said that the second cylinder's valves are simpler, and that is because of the speed regulator, a genius piece of engineering that we haven't looked at yet. Remember that our steam engine does not have a throttle like the model does. It just has a central opening valve, not a particularly precise control method. And that is a problem, because the purpose of this machine is to generate electricity, and as the demand on the electrical grid it powers can change, so does the load. If the steam input was constant, the whole assembly would start slowing down if, for instance, a big electric pump turned on somewhere in the factory, risking to collapse the whole grid. So, throttling this by hand using a valve is not feasible. And for this reason, this 120-year-old machine is equipped with, believe it or not, an auto throttle. The device that detects the current speed is called a centrifugal governor, and it's located in this oil-spitting rotating drum. Inside of it, two weights rotate around a shaft, the centrifugal force pushing them outwards while their weight is pulling them down and thus inwards. As the rotation gets faster, the increased centrifugal force begins to win, and the weights are lifted, shifting a lever, which in this picture is simply connected to close a valve. However, the way this is implemented in our steam engine is much more advanced than that. Instead of acting on a global valve, the centrifugal governor is connected to the first cylinder's inlet valves, precisely regulating every blast of steam entering the machine.
Okay, the regulator is connected with this rod, this axle. This axle has an extent which changes over this mechanism, the movement of this rod. So this rod is controlling this part, and this is defining the opening time.
While the machine is stopped, we can manually lift up one of the many counterweights in this mechanism to see how the regulator's action is transferred to the valves. Lifting the counterweight disables the inlet valves. I've adjusted the footage's speed and direction to demonstrate exactly how the regulator's action is affecting the component opening the valve. To see this in action, the team was so incredibly kind to turn on the machine once again after the other guests had left, just so that I could film this better. In this shot, Hosper manually pulls on the counterweight to simulate the regulator coming into action. Listen carefully how the hissing sound stops and the machine slows down until, when Kasper releases the counterweight again, the hissing returns but longer, bringing the machine back to its target speed on its own. I was completely blown away by this, so Walters used the main valve to slow down the machine to a speed where we could neatly see the first cylinder's inlet valves reacting to the regulator. Again, watch and listen as Walters pulls on the counterweight of the regulator, simulating it coming into action. Isn't this just insane? And just like that, you now know the secrets of this crazy system, which, in hindsight, wasn't quite as hard to understand as you might have thought at first glance. Would you agree? Let me know in the comments. But even though we now have covered the steam engine itself, we still even haven't touched the purpose that it has, generating electricity. But this video is already long enough, so let's finish it off with a few more shots of this stunning historic machine and cover the generator in a second video. A huge thank you to the members of TGV ZU who, despite having had many visitors on this day, devoted a lot of their time to this video, showing and explaining everything with great passion and patience. Thanks for watching and see you in the next video about the generator, another genius piece of engineering. Bye bye and have a nice day.